Hello, this is Eric White. This is the next screencast in this series on writing recursive pure functional transformations. And this screencast is on purity. Functional pureness is so important that pureness is actually right in the title of a recursive pure functional transformation. It's a very important concept to writing these types of transformations, and I'll give you some idea of why in this screencast. I'll demonstrate some things that show this. So what do we actually mean by functional purity? The idea is that you never change variables, you never change state, you never change fields in an object that is of a certain class. In other words, if a variable is there, or if a collection is there, and that variable or collection is in scope, then that variable or collection will have that particular value or set of values and only those values. It won't change on you. This means that when you write these functional transformations, you never rely on state. It means that if you call a function with a given set of values as arguments, then you are always going to get the exact same results. Now, as an aside here, for those developers who are writing unit tests, this is the best situation you could ever possibly have. You can write a whole bunch of unit tests for a particular method or a particular function, and you can test the results of that method or that function, and you can prove that that method or function works exactly as you intend it to. So let's take a look at some examples and see exactly why violation of purity is not a good idea. So here is a little C# example that is very much not pure. What we can see in this C# example is that we have a source collection that has the values of 1, 2, and 3. And in this source collection, the first thing it does is it goes into a select extension method. And in this select extension method, it sets current value equal to the current item. And then it returns that item. So this is really an identity select extension method, except that it is having a side effect where it is setting the current value equal to the item. And in the next select extension method, it adds the current value times 2 to a running total and prints out the running total. And then it returns that item times 2. And if you look at this code, you can see that what this is going to do is it's eventually going to print 2, 4, and 6 because it's going to be printing each one of these items times 2. And the running total will be 2 plus 4 plus 6, which is 12. So let's run this little example. When we run it, we see what we expect to see. We can see the running total, which is 2, 6, and 12. And we can see the values returned by the second select, which are 2, 4, and 6. But what happens here is, let's suppose that in this query we decided we needed to order the resulting values that come out of the select. So let's .into .order by descending. We want to see them in reverse order. And now if I run it, we can see that our results of the select are as we expect them to be. In other words, 6, 4, and 2. So we got our order by descending to work properly. However, the running totals changed to 6, 12, and 18. In other words, the reason we can see this is that by the time we get into the second select here, we've already materialized the first collection coming out of that first select because we called order by descending, and because we materialized that, the current value is equal to 3 when we come out of that, so therefore it calculates 18 for the final total through the running total. An order by descending shouldn't make a material difference in the result of our running total. And so this shows that we've actually got something put together incorrectly in this particular situation. Now, this is a very obvious example. We can even see exactly what's happening. We can see why it's happening. But in the real world, when you are writing really elaborate transformations and you have a little bit of state outside of your transformation and you are modifying that state somewhere in your transformation, you might be able to get it to work. But then there's going to be another programmer who wants to maintain your query or alter your query, and they're going to come in and they're going to do something that's going to break your query in very subtle ways. And the process of finding that bug is going to be a very painful one because the resulting data that is different happens at a different place than where your query is. It's going to happen after your query is all over and after it's been evaluated. The location in the source code is going to be completely different, that your bug is happening at some place deep inside your query, but you're seeing the results of that at a whole nother place in the source code. And it's going to happen at a different point in time. So in other words, you're running the query and then you see the results of the query afterwards. And this is the worst type of bug where you have the lack of proximity in the source code, you have the lack of proximity in time, and you have the lack of proximity in your abstractions. It's like your bug shows up at a different place from where you actually created the bug. So here's the exact same program in JavaScript. And if I run this program in JavaScript, we can see the first iteration runs exactly as we expected it to. And if I alter this example, if I alter the example in the exact same way and run it again, we see the exact same bug. So in this particular circumstance, the bug in JavaScript shows up in exactly the same way as the bug in C#. I'll show you another example in a bit where it doesn't. Here's another example of a program that violates the principle of purity. This is a program that uses linked XML. The idea here is that the developer wanted to look for the numeral 4 in this collection and delete that item in the middle of the collection. And at the same time, they wanted to print out every item in the collection. So they're iterating through these items that have the value 3, 1, 4, 1, 5, 9, and they want to see that item 4. They want to remove it from the collection. And so they're expecting to see 3, 1, 1, 5, 9. And if I run this example, we actually see the values 3 and 1. And the reason that we see those erroneous results is that in linked XML, underneath this root element, it maintains a linked list of the child elements. And the elements access method here is iterating through all of those child elements. And when in the middle of iterating through those child elements, the code removes an item in those child elements, it basically disrupts the integrity of that linked list. So this is a case where the code is modifying a collection at the same time that the code is iterating through that same collection. Again, this is where the problem shows up in a very apparent way, but there are certainly ways that you can write such code where the problem will show up much, much later or only once in a very long while. The idea is you just don't want to do that. Actually, when I work with XML, I work in general with the principle that I never want to alter an XML tree. I always want to produce a new transformed XML tree. Now, in C# and in JavaScript, this means that we're allocating a lot more temporarily used objects when we write code in this fashion. But you know what? The C# garbage collector is explicitly made for this scenario. If you go back and rummage through some of the old TechEd sessions or some of the old PDC sessions, you can find some sessions where the developers go into the design of the .NET garbage collector in detail and talk about how they made a multi-phase garbage collector such that this multi-phase garbage collector is specifically designed to enable you to allocate thousands and thousands of items that are going to live for a very short amount of time. And the garbage collector will perform really, really well in those scenarios. And they use all kinds of really sophisticated techniques in order to do that. And at the same time, they then move items out of this kind of initial first phase garbage collection into the second phase garbage collection if those items happen to live through 1 or 2 or 3 cycles of garbage collection on the first phase. It's a very intelligent design that is made to perform very well when you are allocating lots of short-lived objects. And in fact, in JavaScript, the exact same thing is true, that the garbage collector is specifically designed for this scenario. And here is the exact same program that is written in JavaScript using the LTXML.js library that I released relatively recently on Codeplex. You can get this linked XML library for JavaScript at ltxmljs.codeplex.com, and it's also based on the very excellent link.js library, which you can get at linkjs.codeplex.com. And here we have the exact same example, and if I run this example with the ltxml.js library, we get a different result altogether. It actually does finish, and it gives the results that developer, using an erroneous technique, expected. And in a way, this is even worse, because if it works in one place, they might expect it to work somewhere else. The idea is that you have to get out of the habit of modifying state. If you find yourself needing to modify state in the middle of a query and you think that this is how you're going to solve the problem of writing this elaborate query, it probably means that you're not thinking about your query in the correct fashion. You need to step back a bit and rewrite your query. There are a lot of techniques that we're going to talk about much further on in this screencast series that enable us to solve such problems. And these will be techniques such as intermediate transforms, where we transform the XML to another form that is easier to work with, or we use custom grouping techniques where we write new extension methods or new operators that group items in a different way so that we can get the results that we want to get. I remember some time ago there was a developer at Microsoft who was talking with me about functional programming and this idea of purity, and they were thinking about how they go about to solve programming problems or how to solve problems that are posed to a developer. And the way that you often solve these problems is you have to solve these in an incremental way. So in other words, you calculate some value, and then you calculate another value, and then you calculate a third value, and then finally you can calculate the value that you really wanted to calculate all along, but you had to do this in stages because it's just too hard to go from point A to point D without going to point B and C in the meantime. And their question was, well, how do you write such code while at the same time writing pure code? And the answer is, when you're writing pure code, there's nothing wrong with declaring new variables and assigning new variables and assigning new variables to those variables. This is something that you do all the time in functional programming. In other words, you calculate intermediate values, and the way you calculate those intermediate values is you calculate them and assign them to a newly allocated variable. And then once you've calculated that new value and assigned it to a newly allocated variable, that variable is now in scope, and you can then use that variable in further parts of your transformation. That's how you solve this problem of calculating intermediate results when you're writing complicated transformations. That's all I'm going to cover in this screencast. Now, I've said in a previous screencast that I'm orienting this series of screencasts towards a couple of developers that I know who are very competent object-oriented developers and who need to write some very interesting functional transforms. These developers, while they're quite familiar with such things as XML and HTML, perhaps don't know all of the various ins and outs and details of the semantics of XML. And this is something that I've been meaning to do for a long time. I have a belief that I can explain every bit of the semantics of XML in a couple of relatively short screencasts. So in order to make this screencast series a complete story, in the next two screencasts, I'm going to record, it's going to be a brain dump of the semantics of XML. And therefore, when we get into the following screencasts where we start talking about the transformations of XML, I can refer to the semantics of XML in a very technically accurate fashion. And it will be based on these two screencasts where I'm going to talk about the semantics of XML that you need to know when doing functional transforms of Open XML. Now, I'm not going to talk about the various semantics of XML that you don't need to know with regards to Open XML, and these are things such as DTDs. We don't need to know about those. I'm not going to talk about XSLT. Well, for one thing, we're using a whole different approach to transforming XML than XSLT. What I am going to do is I'm going to talk about the semantics of XML that you need to know in order to do these functional transforms of Open XML. So see you next time in the next screencast.